All right, let's dive in. Today, we are opening up the rulebook of the universe itself, thermodynamics. Seriously, this is the science that explains pretty much everything, from how your car engine works to how a star burns. And it all starts with a few basic ideas: temperature, energy, and work. So let's start with something we think we know. We use words like hot and cold all the time, every single day. But have you ever really stopped to think about it? When a thermometer shows you a number, what is it really measuring? Turns out that simple little number connects to a law of the universe that's incredibly deep and fundamental. You see, before we can even begin to measure temperature, we need a rule that makes measurement even possible in the first place. And this rule is so basic, so essential, that scientists actually came up with it after they had already named the first and second laws. So they had to go back and call it the Zeroth law of thermodynamics. Okay, let's break down what we're looking at here. In this first diagram, part A, imagine you have two boxes, A and B. They're separated by a wall that's like a perfect thermos. No heat can get through. They can't talk to each other directly. But look, both of them are touching a third box, C, through a wall that does let heat pass. So what happens? Well, over time, A and C will settle down to the same temperature, and B and C will do the exact same thing. We know they've settled because things like their pressures stop changing, they've reached a balance. Now check out what happens in part B. We take system C away, and we replace that insulating wall between A and B with one that lets heat flow. And what happens next? The amazing thing is, absolutely nothing. Not a thing changes. No heat flows, nothing. Why? Because A and B were already in balance with C, which means, and this is the cool part, they were secretly in balance with each other the whole time. And that, right there, is the crucial point. This is the law that actually defines what it means for two different things to have the same temperature. That third system, C, well, that's our thermometer. It's the go-between that lets us compare the temperature of A and B without them ever needing to touch. It sounds simple, but this elegant rule is the logical foundation for every single temperature measurement we make. Okay, so the Zeroth law tells us how to measure temperature, but it doesn't tell us what temperature is on a microscopic level. When two things are in thermal equilibrium, what property is actually the same between them? The answer to that lies in a concept called internal energy. This image really gets to the heart of it. Picture the gas inside this box. It's not just sitting still, right? It's made of countless molecules just whizzing around, bouncing off each other, bouncing off the walls in this constant chaotic dance. Well, the total energy of all that random microscopic motion, that's what we call the system's internal energy. It's the hidden energy that temperature is really a measure of. And this energy isn't just one thing. It's actually the sum of a few different types of motion. You've got translational motion, that's the molecules literally flying across the container. You've got rotational motion, where they spin around like tiny little tops. And for more complex molecules, you even have vibrational motion, where the atoms inside the molecule jiggle back and forth. You add all of that up for every single molecule, and that's your total internal energy. Now for a really, really key idea. Internal energy is what we call a state variable. And the best way to think about this is like your location on a map. Your GPS coordinates tell you where you are right now. It doesn't matter if you took the highway or some long, winding scenic route to get there. Your final location is just your final location. It's the same thing here. A system's internal energy only depends on its current state, its temperature, its pressure, not the journey it took to arrive there. Okay, so we've established that a system has this thing called internal energy. So what's the next logical question? Well, how do we change it? How can we add energy to a system or take it away? Thermodynamics tells us there are exactly two ways to do it: heat and work. And this diagram shows those two ways perfectly. In picture A, we're adding energy to the gas by touching it with something hotter. That's a thermal interaction. But in picture B, we're adding energy by physically pushing down on the piston. That's a mechanical interaction. Now, in both cases, the internal energy of the gas goes up, but the way that energy got there is completely different. So let's get really precise here. Heat is energy that's transferred because of a temperature difference, and work is energy that's transferred through some kind of organized mechanical force, like that piston moving. The most important thing to get here is that heat and work are not things a system has. They are processes. They're verbs, not nouns. They describe energy that is on the move. And this right here, this is probably the most important and honestly, the most commonly misunderstood concept in all of basic thermodynamics. We have to be super careful with our words.
there's a huge difference between the energy a system has and the energy that you do to it to change it. This table lays it all out nice and clear. On one side, you've got internal energy, which we label U. That is a property a system has. It's a state variable. On the other side, you have heat, Q, and work, W. These are not properties of a system. They are processes. They describe energy in transit. Saying a system has heat makes as much sense as saying a person has a punch. No, you don't have a punch. The punch is the action of transferring energy. You know, this quote from the source material just says it perfectly. A gas in a given state has a certain amount of internal energy, but it does not have a certain amount of heat or a certain amount of work. Heat and work are just what we call the energy while it's crossing the boundary into or out of the system. Once it's in, it's all just internal energy. So we know we can change a system's internal energy by doing work on it or by adding heat to it. This all leads to a final, really powerful question. Where does that energy actually come from? If we're just moving it around, does that mean the total amount of energy in the entire universe is always the same? Well, that is the core idea of the first law of thermodynamics, and it's exactly what we'll tackle in our next explainer.